Hello everyone, today we're going to review the rules for differentiation, starting by looking at polynomials. This is something that a lot of you will have done when you were in Year 11 studying Unit 1 and 2 maths methods, but we're going to go over them today. Remember that when we are differentiating, it's a method to find a function which describes the gradient of a curve. So we know from previously that if we just have straight line graphs, we can calculate the gradient by using rise over run, or y2 minus y1 over x2 minus x1. This only works for when we have straight line segments. So the purpose of differentiation or differential calculus that we're looking at today is so that we can find the gradient of any curve. If we're looking at a curve like this, hopefully you can see just by looking at it that we actually have different sections. We have a positive gradient here at the start, sloping up. We have a zero gradient in the middle, a negative gradient, zero gradient, a flat section here again, and a positive gradient. So we can see that for this function, it does not have one consistent gradient. Our linear function we looked at to start with, this one here, it might have a simple numerical value for the gradient. For example, perhaps the gradient of this one equals a half. But in the case of every other function we look at, the gradient changes at different points, and that's what we use the derivative for. So let's get started. In terms of notation, this is something that we want to think about carefully because it's very important that we display our working out correctly and that we're very clear about the difference between the original function and the derivative function. So if we are given a function like f of x equals, we indicate the derivative by using f dash of x. And it is important we include that dash. This means that we've got the gradient function or the derivative function. If our original function is y equals, then we would indicate the gradient by using dy dx. We do need to be consistent with whatever they give us in the question, that we use the same form of notation in the answer. If we're given d dx of something, so for example, you'll be asked d dx of 2x squared plus 3x. What that is saying to us is find the derivative with respect to x of 2x squared plus 3x. So we would just work that out as the actual answer. We don't need any notation. We just write this as the answer. Or the answer in this case, I mean the derivative function is what we would write. The statement says find the derivative, d dx means find the derivative with respect to x of the function in brackets, and so then we just write that derivative here. So let's look at our rules. You will recall these from before. In each case here, we're using these rules where n is an element of Q, where n is an element of Q. So that means n can be a fraction or a negative or a positive whole number, but it must be a rational number. So our value of n is a rational number. That's what these rules work for. Okay. So what our rule is that we take our power and we multiply by our power, and then we subtract 1 from the power here. If I have a constant out the front, like our value of a, this just means a times x to the power of n. So we'll have a times, we multiply by the power n, and we subtract 1 from the power, which would just give us a n x to the power of n minus 1. In our last example, if y equals c, so c is a constant term, this could also be written as c multiplied by x to the power of 0. Remember, anything to the power of 0 is 1, so this is essentially the same as us saying c times 1, so we haven't changed the original expression. Following the same rule as before, to find the derivative, I multiply by the power and then subtract 1 from the power. But if I'm multiplying something by 0, I'm just going to end up with 0. So this means that whenever I find the derivative of a constant term, we will always get the answer 0, regardless of what the constant is. So for our first example, we want to differentiate this expression here. Because we've been given y, our derivative is going to be dy dx. So following the rules we've given before, our 5 is like our value of a here that we can ignore. Our rules say we multiply by the power and subtract 1 from the power. In our second term, 2 is a constant value we can ignore. We multiply by the power and we subtract 1 from the power. And finally, the derivative of a constant on its own is equal to 0. If we simplify this, 5 times 3 gives me 15x squared minus 4x, and that's our function that we're looking at there. We mentioned earlier that the gradient relates to the derivative function. So how exactly does it relate? It expresses the gradient at any point along the curve. So if I have a function f of x, if the gradient f dash x, if the derivative f dash x is less than 0, then we have a negative gradient. So if the value we get is less than 0, if it's negative, it slopes down and I have a negative gradient. If f dash x, if our gradient or our derivative function equals 0, then I have a 0 gradient, and the way we display a 0 gradient, those are the horizontal flat sections of our graph. And if our derivative function f dash x is greater than 0, then I have a positive gradient and my graph will be sloping upwards. So these are the three cases that we have when we're looking at the gradient and the relationship between the gradient and the derivative. Strictly increasing and strictly decreasing functions are slightly different. The definition is written there, and we'll unpack that together now. If we had a set of axes in the Cartesian plane, x and y, our definition says a function is strictly increasing on an interval where x2 is bigger than x1, so where I plot the point x2, it's larger than the value x1. And that implies that f of x2, so the y value of x2, is bigger than the y value of x1. And if we're looking here, this, if I was to connect these together, it's got a positive gradient. The difference here is that if I also have a point of 0 gradient, that is included within this domain, within this range of values. We'll look at an example to hopefully make some sense of this. Strictly decreasing functions is implying that if I have a value of x2 which is bigger than a value of x1, then my y value of x2 is going to be smaller than my y value of x1. So when we're doing a decreasing function, we can see that that largely corresponds with having a negative gradient. However, as I said, we do actually include points of 0. So if my gradient, say I had a function looking something like this, at this point x1, yes, the gradient is 0, but we would say that it is strictly decreasing for the interval from x1, including x1, to infinity. So we do include the point of zero gradient when we're talking about strictly increasing and strictly decreasing. So that's something to keep in mind, and we'll have a look at that. So in our picture shown here, we've got a cubic function shown with some turning points labelled and some questions that we have to answer here. So we want to know, for which values of x does g of x have a positive gradient? Remember, positive gradient means that it's sloping up, so it has a positive gradient for this section here, and it's also sloping up for this section here. When we're talking about gradients, we do not include the points of zero gradient, because in that case it doesn't have a positive gradient, it has a zero gradient. So let's list this here. So does g of x have a positive gradient? That would be for the values where x is smaller than -3 in union with x greater than 2. Or the other way we can say that, if we wanted to write it in interval notation, it would be, we don't include the -3. So if we were saying this in interval notation, we would have the interval from -∞ to 3. We don't include the 3, and, don't include the 3, the -3, in union with 2 to infinity. The next question asks, for which function is g-x less than 0? So that's asking us, where is the derivative less than 0? That's the same as asking, where is the gradient negative? And looking in our graph, hopefully we can see that that occurs in the middle section, so it's occurring in this part here. That's where we've got a negative gradient, or where the derivative function is less than 0. Once again, we will not include these points of 0 there. We can write it in whichever form we like, so we could say -3 is less than x is less than 2, or if we were writing it in interval notation, it's the range of values from -3 to 2. Once again, we don't include the -3 or the 2. Where does g of x have a zero gradient? It has zero gradient at the points -3 and 2, exactly those points only. Now we get into our strictly increasing and strictly decreasing, and this is where it's slightly different. So if we answer our option D first, strictly increasing is generally where we have positive gradients, but we include points of zero gradient. So this function is strictly increasing, so my y value is greater than my x value for the range of values from -∞ to -3, but we include the -3 in union with 2 to infinity. Or in our other notation, we're using less than or equal to signs, greater than or equal to signs. Our strictly decreasing, once again, for strictly increasing and strictly decreasing, we do include points of zero gradient. So we would write it as either from -3 to 2, including those values, or we can write it with our set notation as -3 is less than or equal to x is less than or equal to 2. Up to you how you prefer, but please notice here, very, very important, when we are asking for values of positive gradient, or where the derivative is less than 0 or greater than 0, we do not include those points at which the gradient is 0, where the derivative equals 0, but when we're doing strictly increasing and strictly decreasing, we do include those values, and they are included in both answers, in both sets. Moving on to some other examples here. So if I want to find the coordinates of the point of the curve which the gradient has a value of 1. So first of all, we need to find the gradient. In order to find the gradient function, we will have to expand this function first. So x times x gives me x squared, x times 3 is 3x, negative 2 times x is negative 2x, so I'll get plus x. Negative 2 times 3 is negative 6. We need to find the gradient, dy dx. We multiply by the power, subtract 1 from the power. In this case here, the power is 1 when it's not written, so I multiply by the power, I subtract 1 from the power, and the derivative of a constant is 0. Notice that x to the power of 0 is equal to 1, so it ends up just being 2x plus 1. The question asks for the point on the curve at which the gradient has a value of 1. I've just found the gradient formula. I want to know where that equals 1, where the gradient has a value of 1. I can subtract 1 from either side to give me 2x equals 0, and then I can divide by 2 to get x equals 0. This gives me the value of x, but my question wanted to be to find the coordinates of the point. So I therefore need to find the y value. When x equals 0, y is going to be equal to 0 squared plus 0 minus 6, negative 6. So therefore our coordinates are at the point 0, negative 6. Let's have a look at another. In this case, we're wanting to find the coordinates of the point of the curve at which the tangent line makes an angle of 45 degrees at the positive x-axis, given that the curve is this function here. Now that might sound a little crazy to you, but what we're saying is here's a function. I want to find the point somewhere along here, so that if I was to draw a tangent, the angle it's making with the x-axis, this angle in here, is 45 degrees. So what I'm interested in is the gradient at this point. Remember that we learnt earlier on, back in chapter 2, that m, the gradient, is equal to tan theta, where theta is the angle made with the positive direction of the x-axis. If I substitute that into this equation, I will get m equals tan of 45 degrees. Hopefully you recall with your exact angle values that tan of 45 degrees equals 1. So this means I'm saying that I need to find the point on the curve at which the tangent line makes an angle of 45 degrees. That's the same as saying I want to find the point where m, the gradient, equals 1. Remember, the other way we can say gradient is dy dx equals 1. So we find dy dx. We've got y equals x squared minus 3x plus 2. To find dy dx, we differentiate, we multiply by the power, subtract 1 by the power, we multiply by the power. We want to know where does the gradient equal 1. We can solve this by adding 3 to each side and then by dividing by 2. Once again, I need to know the coordinates, so we need to substitute this into our original equation to find the value of y. So we will get 2 squared minus 3 times 2 plus 2. So that will give us 4 minus 6 plus 2, which is equal to 0. So therefore, at the point 2, 0, the tangent line, like I drew over at the start, would make an angle of 45 degrees with the positive x-axis. The final example for this session, we're looking at the opposite of example 4. We're trying to find the angle that the tangent line makes with the positive direction of the x-axis. So this time we're saying we've got a curve, whatever it might look like, and we want to know at the point 1, 0, wherever that might be, if I was to draw a tangent line, whoops, let's pretend that actually touched there, a tangent line, what is the angle it's going to be making with the positive x-axis? Once again, we need to use our helpful formula m equals tan theta. Theta this time is what we're trying to find. In order to use this equation, therefore, we need to have something to substitute in for m. Luckily, we can find that. if we differentiate our function, multiply by the power, subtract 1 from the power, multiply by the power, subtract 1 from the power, we want to know the gradient at the point 1, 0. So if I substitute in when x equals 1, we will get that the gradient is equal to 4 times 1 is 4, minus 2 times 1 is 2. The gradient is equal to 2. Remember, dy dx is the same as m. Both are different ways of expressing the gradient. So what we're saying, therefore, is that I need, if when we use m equals tan theta, at this point 1, 0, the value of m, the value of the gradient, is 2, and that will be equal to tan of theta. In order to get theta by itself, we have to calculate inverse tan of 2. Now this is not one of the exact angle values that you're expected to know without your calculator. So what you will need to do instead is to use your calculator. When we're asked to find angles made with the x-axis, generally this is one of the few times where we do this in degrees rather than in radians. So you get your calculator into degrees mode, you would find inverse tan of 2, and that in your calculator would give us 63.43 degrees. Please check on your calculator to make sure that you can get that as well. And that's all for this time. Thank you very much for listening.